Hello everyone. Today we are going to talk about section 4.6, dimension of vector space. Before we start solving examples, I want to refresh information which we learned from lecture. So actually we proved a couple of theorems. Theorem number 1 was about number of vectors in bases, different ones, for vector space V, finite dimensional. Finite dimensional means that that's just not like infinitely many dimensions in it. We proved the theorem that all bases are going to have same number of vectors. So if one basis has 3 vectors, all other bases are going to have also 3 vectors. They can be different, but amount of vectors is going to be the same. Because of that theorem, we can count this amount of vectors in the basis, and because it's the same for all of them, we can name this amount of vectors dimension. And usually we are going to put dimension, in parentheses we're going to put the space, and then just number of vectors which are in the basis of V. It's 3 vectors, 3. If it's 10 vectors, 10 vectors. We are going to set dimension of zero space, which has only 0 vector, as 0. Okay. And the second theorem was about arbitrary sets of vectors in a vector space. Imagine that we have vector space V, and the basis is given by n vectors, v1, v2, v3, vn. Now, let's consider some other sets of vectors. I don't know, just some other set. There are going to be 2 things which are true about this set. If that set has more vectors than n, for example, n plus 1 vectors, or n plus 2 vectors, or n plus 10 vectors, this set is going to be linearly dependent. So actually, if basis has 3 vectors, all sets of 4 vectors, 5 vectors, 10 vectors are going to be linearly dependent. Second, if set has less than n vectors, it won't be able to span V. It doesn't span V. So for example, if you have a 3-dimensional space, any set of 2 vectors is not going to span it, no matter how good are the vectors. Even vectors which are going to be linearly independent, they're still not going to span V. Okay? So that's going to be the second theorem we kind of proved in this section. Now, let's do some examples. So I'm going to start with first finding dimensions of familiar spaces. For example, what is, let me label example 1. What is dimension of space Rn? Like R2, R3, well, it's obviously n, because we can use the standard basis vectors like, ij or ijk, or like e1, e2, e3, en, which consist out of 1, 0, 0, or 0, 1, 1, and so on. And it's going to be n of them. So standard basis has n vectors. Remind you, what is standard basis? I'm going to write down e1 equals 1, 0, 0, and e2 equals 0, 1, 0. And because we have n positions here, we are going to have n different standard basis vectors, and we are going to count them, just n of them, so dimension is n. So what is going to be dimension of polynomial space? Polynomial of degree less or equal than n. And dimension of polynomial space, polynomials of degree less or equal than n, is going to be equal n plus 1. Why? The basis is going to be 1, x, standard basis, x squared, and x to the power of n, right? So in total, we have n plus 1 different edges here. What is going to be dimension, for example, slightly different vector space? So dimension of a space of 2 by 2 matrices. Well, if you guys remember, standard basis consists out of bunch of matrices with 1 in a different position, right? How many of those matrices are going to be? 4, actually, right? I'm going to remind you, M1 is 1, 0, 0, 0, and M2 is 0, 1, 0, 0, and so on. In total, there are going to be 4 different matrices. Again, standard basis here has 4. Well, if you have a different dimension of a like matrix space, it's going to be a different number here, right? If you have different size of the matrices. Now, guys, what other vector spaces do we know? Remember that solution of homogeneous equation ax equals 0. It's also vector space. Solution x. It's a vector space. How do we know this? Well, let's just, maybe you guys already forgot this, but let's kind of review. Remember that if you do have two solutions of homogeneous equation, x1 and x2, the sum of these two solutions is going to be ax1 plus ax2, and it's going to be 0 plus 0, it's still 0. So if you have a solution, if you have two different solutions of homogeneous equation, the sum is still a solution. Also, if you multiply a solution of homogeneous equation by a constant, you can always take this constant outside. I'm going to use x1. And this way, constant multiplied by 0 is still 0. So it's still solution. So this space is closed about like addition, scalar multiplication, and other stuff is going to work too. We kind of proved it once some time ago, but I'm afraid that you forgot this. So solutions of homogeneous equation are making vector space. Now, how to find what is dimension of that vector space and what is the basis? Well, I'm going to consider a very simple system of linear equations as example. Let's consider next system. 3x1 minus 2x2 plus 5x3. And my system is going to be just one equation. So if I divide by 3, this equation, I'm going to get what? x1 minus 2 over 3x2 plus 5 over 3x3 equals 0. We have one leading variable and two free variables. I'm going to set them up as like parameters p and, I don't know, t, for example. Again, if you write it down as a matrix, the matrix is going to, let me write it down as a matrix, it's going to be 1 minus 2 over 3, 5 over 3. That's going to be the matrix. Well, that still works. I'm using this example as a very simple one. Now, if I want to solve for x1, I'm going to have what? x1 equals 2 over 3 p minus 5 over 3t. Now, guys, what I'm going to do, if I want to kind of represent my solution x1, x2, x3 as a sum of vectors or like in vector form. I'm going to write down first all solutions like this, right? That's like all like how solution looks. P and T here are arbitrary constant, right? P and T are just any real number. Now guys, what I'm going to do, I'm going to write it down as a vector. I'm going to write down like this. x1, x2, x3 equals. Then I'm going to write down over here P, and the coefficient of P for x1 is 2 over 3. For x2 is 1, and for x3 there is no p here, that's 0. Plus t, and for the first one it's minus 5 over 3, for the second one is 0, and for the last one is 1. So what we have, guys, we have a linear combination of two vectors. This is v1, and this vector is v2. So we have like p v1 plus t v2. And p and t are just arbitrary numbers. What is this? That's linear combination, right? Linear combination of v1 and v2. Well, we know that linear combination is kind of all possible linear combinations is making a span of v1 and v2, right? So basically, the space of solution is a span of these two vectors. Let's look at these two vectors. Are they linearly dependent? Well, even like just simple analysis is going to show that they're not linearly dependent, because like for two vectors to be linearly dependent, they're supposed to be multiples of each other. For example, you multiply first vector by some number, get the second one, but it's impossible to multiply this 0 by anything to get this one. So they're linearly independent. Well, so they are making a basis, because all vectors can be expressed through these two vectors, and kind of they're making a basis. just because they span and they are linearly independent, they are making basis. And how many vectors do we have in basis? Dimension of this vector space of solution is 2 because we have 2 vectors. Remember again what basis is. Basis is a set of vectors which spans space and linearly independent. We see that they're linearly independent, and the formula actually itself tells that it's going to be a span. Well, that was a very simple example of like finding dimension. Okay, let's consider example 3. For example 3, I want to consider some just like some weird spaces. For example, consider all vectors from R4, four-dimensional space, of the form A, B, C, 0. So kind of arbitrary numbers as the first 3 coordinates and 0. They are making subspace of four-dimensional space, right? Well, because you add them and you are going to get the vector back, and you multiply them by a number, you're going to get the vector back, so it's closed under addition multiplication. So what is going to be dimension of this space? Well, what we can do, we can introduce a standard basis of this subspace. And standard basis can be next. 1, 0, 0, 0, right? 0, 1, 0, 0, and 0, 0, 1, 0. And you can express all vectors of this form through the basis as a linear combination looking like this. A multiplied by E1 plus B multiplied by E2 plus C multiplied by E3. If you label this one E1 and this one E2 and this one E3. So all vectors of this shape A, B, C, 0 can be kind of expressed as a linear combination, right? So basically these 3 vectors, what? Linearly independent, right? Well, obviously kind of linearly independent. Second, they span actually this space, right? Just because you can express all vectors in this space as a linear combination. So they are bases. Bases, right? And how many vectors you have? Dimension is number of vectors, right? Well, I'm going to just label it the space as V, so dimension is 3. Okay. Well, all those questions were about like kind of around first theorem we had, right? What about second theorem, that the vector sets are going to be linearly dependent if they have more than n vectors, or they are not going to span or not be a basis if they have less than n vectors? Well, that theorem can be used, or like can give us an idea of how to create a basis if you do have some vectors. Imagine somebody gives you 2 vectors, v1 with coordinates negative 1, 2, 3, and v2 1, negative 2, negative 2. They are belonging to what? R3 space, but they don't span it, just because dimension here of R3, oh sorry, 3 is supposed to be below, or no, actually 3 is supposed to be here, is equal to 3. So we need 3 vectors to make a basis. So these 2 vectors are linearly independent, but they are not making a basis because there are not enough of them. They don't span. Well, what we can do, we can add one more linearly independent vector to this set, and then we are going to turn it into a basis. Well, there are many ways to do linearly independent. I'm just going to do a simplest way. I'm going to take vector v3 as a sum of vectors v1 and v2, but I'm going to change one coordinate. I'm going to do it like 0, minus 1, 1, 0, 2, minus 2, and well, 3 minus 2 is supposed to be 1. I'm going to use 2 here. You guys can check at home that v3 is going to be linearly independent with this, and use my trick when you kind of create actually like linearly independent vectors. Okay, well, it's kind of mostly obvious, like, but again, you can check, verify it yourself. Okay. Okay, I think that's all for examples over here. We're going to learn better techniques of finding bases in like, not next section, but section after next.